So let me start with matrix rank. This should be something that's familiar to everyone. And so if I look at, say, P by Q matrices, what are the rank 1 matrices in here? The rank 1 matrices are precisely the ones that look like which you get by multiplying a column vector with a row vector. Is that correct? Yeah, this is what rank 1 matrices are. Okay, so I'm going to call this set S because I want you to think of it as the simple matrices. Okay, the basic building blocks of matrices. And I want to say for any matrix, its rank is the smallest integer, such that you can write this matrix as a sum of rank 1 matrices. Is this a familiar notion of matrix rank? It agrees with whatever your favorite definition of matrix rank is, and I think there are so many definitions of it. But let's hold on to this one. Now, let me give you the definition of tensor rank that's very similar to this in exactly the same way. So in tensor rank, I'm going to consider just this guy for the moment. I will just consider 3 tensors, and I will keep calling this 10 n3. The n stands for the local dimension and the 3 for the number of tensor factors. Okay. Now inside here I will define the set of simples, which is going to be the set of all rank 1 tensors, which is all tensors that look like V tensor W tensor Z. Yeah, does that make sense? This is what simple tensors are. And now tensor rank, so if I take some tensor in here, its tensor rank is defined as in exactly the same way, minimum of R such that you can write the tensor as a sum of simple tensors. Yeah, sounds familiar? Okay. Now I want to make this connection very precise, that matrix rank is the same thing as tensor rank for 2 tensors. Okay, so the analogy, or not even analogy, the way to identify it is you take n by n matrices and you identify it with, or maybe let's just do P by Q matrices, and let me just write 2 tensors here. I identify P by Q matrices with tensors CP, tensor CQ, and the identification is kind of straightforward. You take, so there is a basis for P by Q matrices given by the elementary matrices, which have a 1 in the ijth entry and zeros everywhere else. I will call that Eij, and this I want to identify with Ei tensor Ej, where Ei denotes a standard basis for this vector space and Ej denotes a standard basis vector for that. Yeah, so this is a clean identification, which just proves that they're 2 vector spaces of the same dimension. But then I say matrix rank will go to tensor rank. Okay, this is something that's not so hard to see. A column vector times a row vector under this translation will go to a column vector tensored with another column vector, if you wish. Okay, there we go. So we will keep switching between the two when we want to. And here's another example of something similar, which is what's called warring rank. And this is the one that we'll focus mostly on. Okay, so I define poly ND. I don't know why I have to do D. Let me just do 3. This is going to be polynomials of degree 3 in n variables. Is that clear? Exactly degree 3. So,
Not necessarily homogeneous.
yeah, I mean homogeneous. Right? And inside here, I will call the set of simples all cubes of linear forms. So you take a linear form and you cube it. And when I say linear form, I mean a linear polynomial in n variables. Okay. So the warring rank of some cubic polynomial is going to be the smallest number, so that you could write f as L1 cube plus LR cube, where the LI's are linear. Okay. So you have some cubic polynomial and you want to write it as a sum of cubes of linear forms. What's the smallest number you need? Okay, this is what warring rank is. And all of these fit inside this, they fit inside this great generality, where you don't really have to worry about what these things are. You just have some vector space and you have a subset of it, which is simples, which you think of as a simple set. And then you consider S hat, which I will call the span of S. Right? It's a subset of the vector space. So take all sums now, and you'll probably get something larger. And I want to say the complexity of something in the span, sort of the additive complexity, or I'm probably going to use this notation rather than that, or I call it the S rank, would be the minimum. So the smallest integer, such that you can write f as a sum of so many simples. Yeah, does that make sense? And it fits in with all three of these situations, where I've happily defined S to be the same set of simples that you want to be thinking of there. And here you just have here you're just in a good situation where the span of the set of simples will be the whole vector space. Right? So the span of rank 1 tensors is all tensors. The span of cubic forms is all degree 3 polynomials. Yes, with right. Okay, so without loss of generality, V is S hat. Okay. So now we come to the question, and the question that we want to say, how can you show, if I give you a certain tensor, I give you a certain polynomial, that its tensor rank or warring rank is high. So you have some degree 3 polynomial, and you want to somehow convince me that you need at least 17 linear forms to be able to write them as sums of cubes. Yeah. So how do you do this? And the way to do it, or at least one kind of strategy, is to use these things called subadditive measures.
So are you actually able to, are you going to be doing this in a general situation, or are you always focused on, I mean, are you answering this question for that kind of generality?
No, I'm just phrasing it in that kind of generality. I will answer the question in these two specific cases, but I will show you what are the features that I'm using, which is not all that much. Yeah, and you might be able to, if you define some new kind of rank or new kind of additive complexity measure, you can just test this technique in 2 steps and see what you will get. And you may get a good barrier, you may not. Depends on what kind of measure you have. Yeah. So in that sense, the technique doesn't really use the fact that we have tensor rank and Waring rank. You can do it for any such thing, and you will get some bound, you'll get some barrier, and that barrier may or may not be meaningful.
Yeah, maybe you didn't start with some introduction about the word barrier you commonly use, but it's going to show that lots of these things are not going to work, proving law.
Yeah, so that's right. I was trying to get there, but the problem then, what are the techniques? So you want to prove lower bounds, right? So maybe let me write this down. Want to prove I mean, this is all complexity is about. You find some model of computation and you want to prove a lower bound. So the subadditive measure is just a map to positive real numbers, non-negative real numbers, which is subadditive. Okay, so it's just a map such that mu of f plus g is less equal mu f plus mu g. Okay, why does such a subadditive measure help you in proving a lower bound? Is the following. So you have the set of simples here, and let's say A is the maximum of, A is the largest of the subadditive measure that you get when you plug in all the simples. Okay, and I will be using A for this throughout. Okay, it's a starting point. So once you have this, now if you had something in here whose rank was 2, right? If you had something in here that was a sum of 2 simples, then subadditivity would tell you that its measure would be lesser than or equal to 2A. Correct? So if let's see, if you had something in here with S rank equal to R, then the subadditive measure applied to this function would be less than or equal to R times A. Yeah, why? Because if you had rank R, that means you could write it as a sum of such simples, and you just plug in the definition of subadditivity and you get this. Each one of these has at most A, and you get this. Okay, so I just want to rewrite this in a funny way. I just want to say R is greater or equal whatever subadditive measure you get on this.
R of F maybe.
Okay, R of F. Why am I doing this? Yeah, is less equal the rank times A. Yeah, that's what R was. So I'm just going to rewrite this in a funny way, that the rank is larger than whatever the subadditive measure gives you on it, divided by the maximum possible thing you could get by putting something in a simple. Is that clear? Now, where do you find such subadditive measures? Okay, there is one subadditive measure that's just there in front of us, and rank S. That is already a subadditive measure, and it would give you the best lower bounds you want. The point is what? You don't know how to compute it, right? So let me just make a comment here, is that rank S is a subadditive measure, but it's very hard to compute. So what might you do? You might say, well, let's just find some easier to compute subadditive measures and see what you can get. And here are the easier to compute subadditive measures, and they're called rank methods. Okay, so I'm going to explain this slowly. I only wrote this up in advance because I want to leave this slide there, not slide. I want to leave this board for the rest of the talk. Okay, so it's not that I want to go over it quickly. So now that we've made something without loss of generality V, I will do V. So you have some space like polynomials or tensors or whatever. You take a linear map into matrices. right? Once you have matrices, you can take its rank and get an integer. So what I've described for you is a procedure that takes any element of some vector space. Using this linear map, you send it to a matrix and then you get a number by taking its rank. Okay, that is blah, blah, blah. Okay, I can't switch.
When you defined the subspace measure, you didn't say it was linear.
It doesn't have to be linear.
Yeah, it doesn't have to be. Yeah,
Right.
you didn't say it. Later.
Yeah, so I'm going to fudge the fact that there's linearity in here, and let's just assume everything is in the linear world. Okay. Okay. So what do? So you take a linear map and then you take rank, and this composition of these two processes is a subadditive measure, right? Because rank is subadditive on matrices. Does that make sense? And so if you just put that same idea here, and you take the maximum possible rank you could get by plugging in a simple, right? Whatever your simple was, whatever your set of simples was, and I call that A again, because I really don't have a better word for it. Then by whatever stuff that I did for subadditive measures, you get this kind of a lower bound. Right? The lower bound was you take the subadditive measure and apply it to the thing that you're interested in and divide by A. And the thing that you're interested in is F, and your subadditive measure is to take rank of the linear map. Yeah, does that make sense? Okay, so that's your lower bound. And now I'm going to make a definition. It's not a serious definition, but I call this the potency. So the potency of such a linear map, or the corresponding rank method, or whatever you want to call it, is going to be the best possible lower bound you can prove. And the best possible lower bound you can prove is you look at what's the maximum you can get out of plugging in anything from that in your subadditive measure, and you divide by whatever the simples told you could be. Does that make sense? Okay. And yeah.
Well, there's a comment to make here. In general, in complexity, we're interested in proving lower bounds for explicit functions, polynomials, tensors, and so on. Here, we don't even care if it's non-explicit. You just maximize over all functions in V. You just wonder whether you can prove a lower bound for anything using this method.
Yeah, okay. So then,
the matrices that you map into should be, I guess, large. Otherwise, the length would be at most.
there we go. So this is the first observation, right? If you try to map into 2 by 2 matrices, there is no way you will be able to prove a lower bound better than 2. Because the maximum rank of a 2 by 2 matrix will only be 2, right? So there's no way you can prove a better bound. So ideally, you want these matrices to be really, really large. Yeah. So that's the vision you should have. You should maybe take 3 by 3 by 3 tensors and try to put a linear map into a million by million matrices, and then try to use this method and see how well you can get.
Another relevant comment is that, this is indeed used throughout algebraic complexity in lots and lots of models. We just gave you 2 examples. Lots and lots of models, and in some cases, and they do give low bounds, some low bounds. In some cases, the blow up is even more than exponential. In the the size of the matrices that actually yield low bounds. So this rank method does not bound at all the size of the matrices you map into. You can do whatever you like, as loud as you like.
Yeah. So there's another thing that you want to think about here is we think matrix rank is easy, but if you have to prove it for a family, you have to prove it for a family of matrices, and these matrices could be potentially very large. So you really have to find some non-trivial way of actually computing the rank of these really, really large matrices in reasonable time and space. And not like an algorithm. You have to prove it, right? So you have to write a proof out on paper if you want to prove a lower bound. Okay. So let me give you a few examples of these things, and they're going to be kind of simple. That's okay. So the first example is kind of the easiest one you might come up with, is you have 3 tensor factors, just club 2 of them into 1. And now you have only 2 tensor factors. So if I club the second and third, well, that's a 9-dimensional vector space. So it just becomes a 9-dimensional vector space. And these 2 tensors I can think of as matrices, right? Okay. Now let's see what happens. If you take a rank 1 tensor, something that looks like V tensor W tensor Z, what does it go to? It goes to V tensor something, right? And that something is W tensor Z, but it's still a vector. So that's a rank 1 matrix. Yeah? So that means the maximum possible thing, a simple thing in here can go to is 1, which I call A. Yeah? And if you take some, generic tensor in here, take some 3 by 3 by 3 matrix with kind of random values and you push it forward, you will get a full rank matrix, right? But the maximum possible rank that a 3 by 9 matrix can have is 3. Right? And so the maximum possible rank you can get for some random tensor in here would be 3. So the best lower bound you'll be able to prove is 3 over 1. Make sense? Okay. So now here comes a slightly more non-trivial example.
And that's, you didn't need a method to do that, because that would be very easy to get the rank lower bound
Sure.
on a tensor. Yeah.
What's the easiest way?
A diagonal tensor.
Why? I mean, what's the argument?
No, the argument you can put a 3 by 3 matrix in there. That's 3 by 3 matrix. Anyway, that's why it's not a very clever.
This is not a particularly clever rank method. Here's a slightly more clever rank method. Okay, and so I'm going to give you a linear map from 3 by 3 by 3 matrices, the tensors, to 9 by 9 matrices. Okay, and the way I want you to think of it is a 3 by 3 by 3 tensor is 3 slices of matrices. Correct? It's a 3-dimensional hypermatrix, so it's 3 slices of matrices. Each slice is a 3 by 3 matrix. So I will call those 3 slices A, B, C. Yeah, and then I will put them into a block matrix of this form. Yeah, it's sort of skew symmetric in these blocks, and I put A, B, C minus A minus B minus C. Okay, now there's some way to prove it, and I'm not going to tell you, and it's an exercise if you get bored, is any rank 1 tensor under this, first of all, this map is linear. You add 2 such things, they just add in the blocks. So any rank 1 tensor will go to a rank 2 matrix. It's not the most obvious thing in the world, but it's an exercise, or just come and ask me afterwards. I'm not going to try and do this now. Okay, and this is actually something very nice. This is one in which it actually goes, all rank 1 tensors go to exactly rank 2 matrices and not rank less equal to. Okay, but if you take some random tensor in here, so if you plug in some kind of random matrices for A, B and C, this will actually be full rank. Okay, just do it. Just pick 3 matrices, put random numbers in there, and it will be full rank. Okay, it's very hard to not make it full rank unless you really try. And so a rank 1 thing is going to rank 2, and a random one is going to rank 9. So this will allow you to prove a lower bound of 9 over 2. Correct? Well, so here's the point. If you have a lower bound of 9 over 2, then you actually have a lower bound of the ceiling of 9 over 2, right? Which is 5. I am going to ignore this ceiling. Yeah, so let's not worry so much about it, but there's always this little bit that you can do, but you can only bump up by 1, not more than that by this trick. But here's a theorem, and this is due to Kruskal, and it's non-trivial, is every tensor in there has tensor rank at most 5. Okay, so this is a fairly involved theorem. It's not the easiest to prove. It's not easy to see. Okay.
It involves case analysis?
Yes, it involves case analysis. Okay, so what this means is, using this particular rank method, you could actually prove that some tensor has tensor rank 5, which is the maximum that you should be able to prove. Yeah, but what it does not mean is, given a rank 5 tensor, this method will prove a lower bound of 5 for you. Okay, so that still doesn't do it, but this is some way to prove that certain tensors have rank 5, which is the most you can hope for. So in that sense, this problem is not so bad for this case, but this is not what we look for in complexity, right? We want to see what happens as n grows. Yeah, I want to increase the dimensions and see what happens. Okay, so what I can do now is I will state the theorem, and I will state the theorem in special cases. So I will do the special cases first, and then I will tell you how to, change 3 to D and 3 to D and all of these things. And this theorem is, of course, due to the aforementioned people, Efremenko, Garg, Oliveira, and Vigderson. And it's in that paper. I've been told it's a little small to read, but the paper is Barriers for Rank Methods in Arithmetic Complexity. Okay? And the theorem is as follows. So suppose you have a linear map from degree 3 polynomials and n variables to matrices. Doesn't matter what size. And then you run that whole story, right? Given a linear map, you could think of it as a rank method, and you want to see what's the best lower bound you can prove. And the best lower bound you can prove, I gave it a name, I called it potency. The potency of any such rank method, doesn't matter what k is, what l is, what the linear map is, doesn't all matter. The potency is less than 2 times n plus 1. Okay? And this, I want you to contrast with what we want, which is what a generic, some random degree 3 polynomial in n variables will have rank about n plus 3 times n plus 2 over 6. Okay? I hope I got the calculation correct.
Random polynomial.
Right. Yeah? So a random one will have this. So that means, there are polynomials in here whose Waring rank is at least this much. This is a quadratic number. But somehow, no matter what rank method you do, you will never be able to prove something better than linear. Okay? And I'm not even giving you a big O or a small O or something. I'm telling you 2n. Okay? So that's the first one. And the second result is the same kind of result, but on tensors. So on 3 tensors, if you take any rank method you want, doesn't matter what, the best lower bound you will ever be able to prove would be less than or equal to 2 times 3n plus 1. Okay, there's a specific reason why I wrote it as 2 times n plus 1 rather than 2n plus 2, or 2 times 3n plus 1 rather than 6n plus 2. Okay, so specific reason is this 2 and this 2 have the same meaning. This n and this 3n have the same meaning, just different context, and the 1 and the 1 have the same meaning.
The n and the 3n are the number of variables.
Yeah, we'll get that. Okay, and what about a random tensor? A random tensor will have about n squared over 3 tensor rank. Yeah, which is again kind of quadratic. This is linear. It's good. So let's just do a fact check. The potency of this guy is the same one in there where n is 3. So the theorem would say, well, you should not be able to prove lower bounds better than 2 times 9 plus 1, 20. Yeah, but the best lower bound you can prove is 5. It's not so bad. Well, there were other reasons for why you couldn't prove a lower bound better than 5, because it doesn't exist. But it's just a sanity check that the theorem isn't telling you things that are false. Okay, so let me see what I want to know. So let me explain some of these numbers here, right? So the 2 comes up from somewhere, the 1 comes up from somewhere, but there's an n here and a 3n here, and let me explain where those numbers are coming from. Okay, so this comes from parameterizations of simples. Okay, so there are 2 cases, right? So first you have Waring rank, so the one above. So you have degree 3 polynomials in n variables. What are the simples? The simples are going to be cubic linear forms, right? So cubes of linear forms. So L is a linear form. Linear in n variables. Okay. So if you think about it, what this means is there is a map from linear polynomials to the set of degree 3 polynomials that takes a linear polynomial and cubes it, right? I will call this parameterization pi, and what's happening is that the image of pi, so let me write it here, image of pi is precisely the set of simples. Yeah, just the definition of what the set of simples is. And then I want you to notice that this guy is a vector space of dimension n, right? Linear forms in n variables is a vector space of dimension n. So what I've done is I've taken the set of simples in there and I've parameterized it with a vector space. So I've parameterized it with n variables. Yeah, it's good. And that's the n that shows up here. Okay. And now you do it for tensor rank. And okay, so let me just be clear here, is I'm doing it for n variables, 3 things. So here I'm going to do it for local dimension n, 3 tensor factors. So how do you parameterize rank 1 tensors here? Okay, we know what the rank 1 tensors are. These are tensors of the form V tensor W tensor Z, where all of these guys are inside, or all of these guys are particular vectors. This already tells you what a parameterization looks like. And the parameterization is Cn tends cross Cn cross Cn. So you have 3 vectors in here, and they go to V tensor W tensor Z. Okay, so this is Cn.
There is a plus there.
Why is there a plus?
You want 3 and seems like the left hand side is cross. I mean, you are not taking all possible things in there.
Sorry, what?
It's not, yeah, you want 3n rather than n cubed values. It's okay.
This is a Cartesian product. It's not a.
Yeah, Cartesian, very good. Yeah, it's not tensor.
Yeah, this is not a tensor product. This is a Cartesian
That's what
product.
I wanted to point out.
Yeah.
Yes.
Yeah, this is a Cartesian product. So what is the dimension of this guy? So this guy here is a 3n dimensional vector space, right? And that 3n is the 3n that shows up here. Okay. So, I mean, these kind of matchings tell you what? They tell you it doesn't really depend upon the situation. It sort of depends upon certain things that, like the parameterization. Yeah. And yeah, okay. So, let's see where I want to go now. So I'm going to give you the proof of this, but before I give you the proof, I want to maybe set up 2 kind of technical things. But they're not really technical. I'm just talking about functions and vector spaces and vectors and rational functions and power series. But for the sake of not getting confused during the proof, let me just do 2 things. So the first thing I want to do is
You really want to write on this board, which you may need to cover.
yeah, I think it's okay. So the first thing I want to do is I want to discuss vectors of rational functions. Okay, so it's not an imaginative concept. It's just maybe not something that you've ever had to use in your life. Okay, so let me do this. So I'm going to start with a bunch of variables. And so if I don't put a subscript, I mean together. Yeah, I don't have the capacity to write bold on a blackboard, but it's a bunch of variables. And then f.
Set or is it a tuple? What do you mean?
Sorry.
Is it like a set?
Yeah, let's say it's a tuple.
Means the vector.
Yeah, it's a vector of variables. It's not really going to worry. So I'm going to call the function field, right? So this is going to be all rational functions in n indeterminates. Yeah, And so the reason I put Z is I will be lazy and I will write this. And you, yeah, so set vector, it's kind of pointless. Clear? Good. So now what I want to do is I want to take a vector consisting of rational functions. Let's say my vector is a vector, let's say it has d coordinates, right? So this is a vector of rational functions. So each fi of z belongs to this function field. Yeah, so you know what it looks like. Good. So now here's a concept that you may or may not know: is pick any one rational function. It's in many variables. You will be able to expand it out as a power series. Maybe not around every point, but you will be able to expand it out of power series around most points. Yeah, this is something that you should know for one variable. You should have seen this for one variable, but it also holds true for several variables. But what does it look like? This is going to look like sum over all exponent vectors. You have some function. So you have some constant, and then you have some monomial. Okay, so I want to explain this notation. This C corresponds to a complex vector. So it's the point around which you have your power series. Yeah. So when I write Z minus C to the E, I mean Z1 minus C1 to the E1, Zn minus Cn to the En. Yeah. And so implicitly I'm telling you that E is an exponent vector that consists of n different numbers, which are going to correspond to the different variables. Yeah, so this is an exponent vector consisting of, I don't like this, non-negative integers, n of them. So far so good. So I can do this around some C, okay? Some C, and generic C will do. Okay? I keep using this word generic. If you don't like it, just think random. And as long as you have a finite number of them, you will always be able to take. So you should think of it not just as random, but random with probability 1. Yeah. So if I have to do more than one function, if I have to expand as a power series for more than one function, as I'm going to try and do for these guys, then I can still pick something at random and it'll work. Okay. So that's what I'm going to do. And let's say that point for which it works is still C. So for all I. So then what does my vector look like?
Can I ask, so
Yeah.
when you're talking about that you can write it as a power series,
Yes.
are you making sort of a statement about these formal expressions that if you just, are you making a statement about actual analytical convergence at that,
I think it holds because I'm only in rational functions, but I don't really need it. I just need it's a rational function. So
so you actually mean it as a function, the left side equals the right hand side,
as a function around some small neighborhood around this point.
as opposed to sort of just expanding the left hand side in.
That's right. So we will only use the latter.
Mhm.
We will not need to worry that these are functions. We will only need that this is a formal equality in the ring of power series or something, but you know, this actually is an issue when you try to generalize this to other contexts. But we are in a simple enough situation where you can actually look at them as equalities of functions. Okay. So you have this vector, and each one of them you write as a power series, right? Each one of them. So it's going to look like sum over exponent vectors f1e z minus c to the e, sum over an exponent vector f2e z minus c to the e, blah blah blah. I don't care where it ends. But now what I want you to do is I want you to observe that I can take the summation out. Right? They're all power series. I can take the summation out. So what will I do? I will write it as sum over f(z)e, f1e, f2e, dot fde, and then I will also take the monomial out of it. The two expressions are the same, right? And now all I will do is I will call this something. So sum over e, f e, of z minus c to the e. Okay, so let me write that out in a happier place. So I wrote this, so what did I do? I had a vector of rational functions and I wrote it as a sum over all exponent vectors. So this fe is a vector, so let me put an underline, times some monomial. Okay. Now here's one thing to point out is, so inside here these guys were complex numbers, correct? In the power series the coefficients are complex numbers. So this vector is a vector filled with complex numbers. Good. So then this guy is a vector inside, is a vector with complex coefficients. Yeah, so good. Okay, it's not particularly hard, but if I throw this at you during the proof, you will get confused. Okay, so the slogan is, if you have a vector of rational functions, you can write it as a vector of power series around some random point. And what can you do with a vector of power series is you can split out the components and write them as a power series looking kind of thing where the coefficients are now vectors. Okay, so it's not so bad to call this guy a coefficient vector. Okay, so we go. So okay, we're there. Now let me give you a hint of the idea of the proof, and then maybe we take a break. Okay, so this is also a good reason to leave it there because I can always pull it up and show people. So we want to prove some upper bound and potency, right? So you will assume what the simples go to. So you will have some a to start with, right? So you will have this, blah, blah, where did I put it down? Right? So you will have the maximum possible thing that a simple guy goes to. And based on this, if you want to prove an upper bound and potency, you have to give an upper bound on the rank of some generic guy. Right? You have to say no matter which one you take, its rank cannot be larger than something. Therefore, you couldn't have proved a lower bound. Does that make sense? So let me write this down a little more precisely. So you start with some rank method and you have this A, which is the maximum possible rank of the simples. Now, if you prove KL, if I prove that rank of phi of f is less equal a times some big number d, right, for all f in your vector space, then the potency will be less than or equal to d. Right? This makes sense? So I start with this hypothesis. And then I try to prove a statement that basically says, well, no matter which element of the vector space you take, you look at where this, you look at the matrix that it's sent to, it can only have rank at most this much by some weird or whatever argument that I have. Then this means that you could not prove a lower bound better than d. Right? So this means your potency is less than or equal to d. So that's kind of the strategy. So if this is the strategy, then you need a way to prove an upper bound on the rank of the images of all these matrices. And here's one way to do it. Here's one idea there is so basically all I'm saying is you need to be able to prove upper bounds on the ranks of matrices. Yeah, those matrices are going to show up in some way, and you have to find some way of proving upper bounds on the ranks of matrices. And here is how you prove an upper bound on the rank of a matrix. It's actually an idea that we sort of saw last time. but you don't have to remember it. So if I have a matrix inside a shape that looks like this, let me see what I wanted. N1 and N2, then the rank of such a matrix is less than N1 plus N2. Agreed? Yes, okay. See this. Yeah. The reason is these many columns can contribute a rank of at most N2. And then what's left is a bunch of rows, and they're at most N1 rows, so they can contribute a rank of at most N1. So the total matrix can have a rank of at most N1 plus N2. Yeah, does that make sense? Okay, so now here's the thing. The observation is that this kind of set of matrices, they form a linear subspace, right? Which means they're robust under addition. Yeah. So here's how you do it. The idea is you start with this data. So you start with, you have this linear map. So let me now just come down to say a specific thing. So you have such a linear map. And then you have this number, which is the maximum possible rank of whatever a simple can go to. Right? You take the set of all simples, you look at the matrices you go to, take the maximum possible rank. So starting from this, I will then somehow show you that the image of all the simples lies inside such a subspace, where this side is, what is it? A times n plus 1, and this side is A times n plus 1. Okay? If I can somehow show you that, just by using the fact that all the simples of rank less equal A, I show you that they must all land inside some such subspace up to a certain change of basis. Right? There's a certain basis I have to pick or whatever it is. If they can land in such a shape, what does this mean? This means no matter what thing you had in your vector space, which is there's all going to be like some sums of these guys, they're going to stay within this subspace. Correct? So it's going to stay within this subspace, which means the rank of anything is less equal this guy plus that guy. Yeah? So it's less equal 2 times n plus 1 times A. And so what does this mean? This is really bad to go upwards on the board, but let's just do it. This means that the potency is less equal this number, which is what anything can go to, divided by A. That makes sense? Which is 2n plus 2 times n plus 1. Yeah, that makes a lot of sense. That's going to be the idea. But the point is, I have to somehow get the right basis, and I have to somehow put it in this shape. Okay. The one thing I want to do is I want to recast this in a slightly different language. Okay, and it's going to be that same thing where I want to switch from matrices to tensors. I want to switch from matrices to 2 tensors, and then I want to throw away the need for. I want to replace the need for a picture with something that doesn't really choose basis. Okay, and here's what it is. And I just want to say this subspace corresponds to, so let's say this is of side K and this is of side L. So this will correspond to some subspace of L dimensional space, and this will correspond to some subspace of K dimensional space. So I want to say this is U tensor CL plus CK tensor, okay, so maybe U1, U2, and I want to say this is U1, this is U2. Make sense? Yeah, I don't really need to choose basis, right? I just need some vector spaces U1 and U2 which have the right dimension. Yeah, and so if you pick a certain basis that, so in this case, U1 would be, the first E times n plus A vectors. Yeah, but it could be anything it wanted, and it would just mean I don't really want to know what basis it is. I just want to be able to find you such subspaces. Okay, so let me write this down sort of precisely. So we start with the same thing. You start with the linear map. Again, I'm going to go to just this one guy. And A is going to be the maximum possible rank that a simple can achieve under this linear map. And then I want to prove that the image of all the simples lies inside this guy. U2, sorry. U2, where dimension of U1 is less than or equal to A times n plus 1, and dimension of U2 is also less than or equal to A times n plus 1. Yeah, is this clear? And then this would prove the theorem, right? Yeah, by that same argument. Okay, so this implies theorem. All right. So what's left is I have to somehow tell you how to conjure up these vector spaces, these subspaces. Yeah. So maybe we take a break and then. Okay. So I'm going to give the proof of the theorem, and so let me just set things up. You have a linear map from degree 3 polynomials in n variables to matrices. That's what your rank method is. And linear is another way of saying it's a degree 1 map. And then you have this parameterization, that's right here, which parameterizes your simples with an n-dimensional vector space, right? So it's an n variable parameterization, and the parameterization is degree 3. Yeah, so maybe I didn't say this explicitly here, but this is a degree 3 parameterization. Okay, so I have this parameterization. What I'm going to do is I'm going to compose the two maps. Yeah, I compose the two maps, and so now what I have is a map from this vector space Cn all the way to matrices, and I can somehow forget about the poly n3 in between for now. So I have this map, and this map is a composition of a degree 3 map and a degree 1 map, so it's a degree 3 map. Make sense? Yeah, it's a degree 3 polynomial map, but it has some nice properties. First thing is, the image of the parameterization is a simple set S. So if you then apply phi, you will just get the same thing as if you, so you start here, the image is S, you apply phi, you get phi of S, right? So you might as well have done this like this. And that means that the image of L is the same as the image of the simple set under this map phi. Yeah, it's not. So all I'm going to do is I'm going to get rid of the map phi and pi and write everything out in terms of L. So A, which was supposed to be the maximum possible rank of what a simple can go to under phi, will now become the maximum possible rank of whatever a point in here can go to under L. Yeah, this is just follows from this guy. Good. So now with that, let me also set up a bunch of things here. So again, Z is going to be variables. And what else do I want? I want this bold F to be the function field. Okay. So the strategy follows this way. You use the fact that rank of okay, so again, when I say beta, I mean the vector. I don't feel like writing bold. So you use this fact, and this is basically the only fact that you'll ever use. And the first step is to upgrade this to a decomposition of the function field. Okay. So what do I mean by upgrade this to decomposition of the function field? I mean, if instead of numbers here, you plugged in the variables z1 to zn, right? then you get a matrix, a k by L matrix, that's now filled with polynomials of degree 3 in z1 to zn. Yeah, and I want to say its rank, because it now contains entries in the function field, right? So I want to say its rank over the function field is also less than or equal to a. Okay, so that's the first kind of symbolic step. Okay, so this is step 1, and then the step 2 would be to go from the function field to power series. So let me write this as rational functions to power series. Okay, and we've sort of hinted at how to do this when I gave you this little spiel on vectors of rational functions, right? That's what's going to happen. I will explain it. And then the step 3 is you get some sort of monomial decomposition. You see, on one side you have a matrix filled with polynomials, on the other side you have some kind of rational function decomposition into rank 1 matrices over that, which you made into power series, and then you can just match the monomials. Okay, so yeah, it's still kind of vague. I will make every step precise. And once you match the monomials, I will tell you how to extract this u1 and u2 that I'm talking about. Right? And when I say u1 and u2, I mean the u1 and u2 that I needed an argument pair. So is that clear?
No, the thing is the bound on the dimension of u1 and u2 will follow from the symbolic decomposition, from degree bounds, which we don't have in the numeric one.
So these 3 steps, so the first 2 steps are very general. They will assume nothing about anything. Okay. From the third step is also kind of general, but you will start seeing the parameterization and the number of variables play a role. And then finally, when I extract out the subspaces, you will see exactly how many things are coming into that subspaces. Okay. So let me do step 1. So what I want to do is I want to say the fact that if when you plug in numbers, you get rank less equal a implies that when you plug in these variables, the rank is less equal a. Okay, but now you have to be careful, right? This is a matrix filled with polynomials of degree 3, but okay, it's matrix filled with polynomials. So you want to take rank over the function field. That makes sense? Yeah, you can't stay in the world of polynomials. You have to go to function field. Okay, so how do I prove this? The proof is, suppose this had rank larger than a. Okay, I'm just going to say the proof because it's kind of simple. So that means there's an a plus 1 by a plus 1 minor which is non-zero. Yeah, and what do I mean by non-zero? It means you compute this a plus 1 by a plus 1 minor, it will give you a non-zero rational function. In this case, it will just be a polynomial. Right? If you get a non-zero polynomial, you could plug in numbers to get something non-zero. You can always do this. You give me any non-zero polynomial, you can always plug in some complex numbers to get something non-zero. Plug in those numbers, and I will tell you that the matrix when you plugged in beta would have this a plus 1 cross a plus 1 minor non-zero. Make sense? Yeah? It's also kind of the same argument I gave last time for linear subspaces and linear matrices. Okay, so that's step 1. But then what does this mean? So one of the things that I did right at the beginning was I told you we can think of matrices as 2 tensors. Yeah, so I will think of this as 2 tensors, and so the fact that it has rank less equal a means I can write it as a sum of a rank 1 tensors. So that means I can write this guy as a sum of rank 1 tensors. So rank 1 tensor looks like this. Yeah, the matrices, but I will write it in the tensor notation because it's easier to do. But let's be careful about this, right? So this was a map into K by L matrices. So this is a K by L matrix here. So it's a K by K times L tensor. So that means this guy is a vector. So A of them is a vector with entries in the function field and K coordinates. And this guy here is a vector with entries in the function field with L coordinates. Does that make sense? Okay, so we found vectors of rational functions. What are we going to do next? We're going to turn vectors of rational functions into vectors of power series. Yeah, just like how I did before the break. So what I'm saying is, for some complex numbers, C1 to Cn, okay, generic will do. You can write each one of these guys as sum over PIE Z minus C to the E. And you can also do this for the QIs. Yeah, I will make a little thing. Now in this power series, this is going to be now a vector with the complex numbers. So this is going to be a vector with complex numbers of coordinates L. And this guy is going to be a vector with complex numbers of size K. Yeah, I will show you this. Oh, okay, so before I do this, let me say this is step 2. Yeah, so you remember? We took a vector of rational functions and we wrote it as a power series whose coefficients were vectors. Yeah? And these coefficients were vectors with complex numbers, complex coefficients. So I do the same thing up there. That makes sense? Beautiful. Okay, so that, so this was the symbolic step. This was the power series step. Yeah, so let me rewrite it in a little bit more careful way. So let me rewrite this as L of Z1 to Zm is equal to sum from I equal to 1 to A. Maybe I put F here just to distinguish the E's and the F's. It's okay, right? A. And I want to replace this guy with this power series. So sum over E, PIE, Z minus tensored with sum over F, QIF, Z minus C to the F. Okay. So this concludes power series. This is good? Okay. But I just want to point out here carefully that these are vectors inside CK, these are vectors inside CL. And remember what our eventual goal is. Our eventual goal is to construct some kind of subspaces, right? And these subspaces are going to live inside C to the K and C to the L, right? These subspaces are going to live inside C to the K and C to the L. And how would you ever describe a subspace? You'd give a spanning set, which means these vectors have to show up from somewhere. Yeah. So where are the vectors starting to show up from? Is there? All right. Okay. So let me take a breath and make sure that I'm not running away. So, all right. Okay. What's on this one? Parameterization. Yeah, maybe the parameterization can be. So can I erase this bit? Vectors of rational functions. Okay. Now I want to do a small shift. Okay, I don't like to see Z minus C on the right hand side. So I will put a plus C on the left hand side. Okay, so I will write L of Z plus C is equal to sum I equal to 1 to A, sum over E, PIE Z to the E, tensor with sum over f, qif, z to the f. This is good. Yeah, it's just shifting of a function. Now, I want you to notice that the left hand side is a matrix that consists of degree less equal 3 polynomials. Okay, so when I just had the variables z1 to zn, then I knew that this was homogeneous degree 3 polynomials, correct? But now I shifted it a bit, but shifting it does not increase degree, right? But it could add some lower terms. Okay, so it sort of really doesn't make that much of an issue, but it's matrix with entries that are, I'm going to say, non-homogeneous, degree less equal 3 polynomials. Yeah, so that means I can restrict to the degree less equal 3 part on this side and not lose anything. Okay, so this thing means I can look at L of z plus c is equal to sum over I in 1 to a, blah blah blah. I have to write this whole thing. Sum over f, qif, zf, and I can take on this side degree less equal 3. Okay, that's what that means. Okay, so now you look at it, right? When you tensor, the monomials will multiply and the vectors will stay vector tensor vector. Does that make sense? Now you can restrict to the monomials that are of degree less equal 3. That means the degree of z to the e plus the degree of z to the f should be less equal 3. Make sense? And I will say degree of z to the e, I will just write degree of e. Okay, so I want to say from this, L of z plus c is equal to sum, and now I will pull all the sums out to the left hand side. IEF, degree of e plus degree of f, PIEZE is less equal 3, tensor QIF z to the f. That makes sense? Yeah? You just took the degree 3 parts that showed up. Okay? And I mean, another way of writing this is I can just move the monomial there. Yeah, it's good. So let me rewrite it without all kinds of spaces in there. Z to the e plus f, PIE tensor QIF. Okay, and this is what I call the monomial decomposition.
PIE are numbers, right?
Vectors. Correct? They're vectors. Yeah. You see, all of this is happening in this function field roughly, right? So the z's, you sort of treat them as scalars and you can move them around. Yeah, a monomial in the z is z1 to the e1, z2 to the e2, blah, blah, blah. This is a scale in this function field. Okay, so that's a monomial decomposition, and this concludes step 3. Yeah, why do I call it a monomial decomposition? These guys are monomials. Okay, so now I just have to tell you what u1 and u2 are and prove that they work. Okay, so now my claim is,
Maybe you can ask people to guess.
yeah, you can guess what is u1 and what is u2. Okay, first let's do this. It's a finite sum.
So I guess the case when E has degree 0 or F has degree 0 is not very damaging, so that
Sure.
you can ignore those, and then
That's one. That would be dimension 1. Yeah.
And
so then the other two, E has degree 1, F has degree 2. That can give you one of the spaces, and
Yeah. Yeah, so let's do it. We don't have to ignore it. I just say you take the span of all these PIEs where degree of E is less equal 1. to write it. PIE. Okay, and you do it for all the i's, right? 1 less equal I less equal a. You see how this a really doesn't play a role. It just shows up in the summation and it's going to run away. Okay, and I'm going to say U2 is going to be the span, not of the PI's, but QIF, such that degree of f is less equal 1, 1 less equal I less equal a. Make sense? Now what do I have to do? I just have to show you that the image of L, which is the same thing as phi of S, right? That the image of L lands inside U1 tensor KL. Okay, so I need to show image of L lands inside U1 tensor CL plus CK tensor U2. Right? It's exactly that one. Does that make sense? Let's do it. It's not so hard. Let me see where I want to go. Is an extra board here? No. Oh God. Fine. Okay. It's funny that I have to use this here. I don't want to remove the theorem there. That's fine. I will just do it here.
It's a local computation.
Yeah, it's a local computation. It's okay. Okay, so let me show you. So I want to show the image is inside something, right? So let me just plug in something inside Cn and show you that it's there. Yeah, if I just show you that L of beta. So to show this is enough to show that, or basically the same thing as showing that L of beta belongs to this for all beta that you can possibly input. Okay, so let me input a beta and see what I get. So I get L of beta plus C, sum of I E F, beta to the E plus F, PIE, tensor QIF. Yeah, I just plugged it in. Now look at any one term. Okay, so take any term. What does it look like? So any term looks like beta to the E plus F, PIE, tensor QIF. Right? So L of beta is a sum of such things. If I want to show that a sum of such things is inside here, it's enough to show that each one of them is inside there. Make sense? Okay, so take one such thing. Now you have two choices. Either degree of E is less equal 1 or degree of F is less equal 1. Why? Because the sum has to add up to 3. If you have two numbers that add up to 3, one of them has to be less equal 1. Okay, two choices. If degree of E is less equal 1, then PIE is inside U1 by definition. So this term, so this guy is inside U1 tensor CL. Make sense? Because this is just a constant. You can push it to this side if you wish, or whatever. I mean, this is in the span, so make sense? And if degree of F is less equal 1, then QIF is inside U2. So then this term would be inside CK tensor U2. Okay? So the terms come in two types. You pick the smaller degree and you put it either on the left one or the right one. Does that make sense? Beautiful. Now what else is left? I have got this decomposition. I just need to find an upper bound on the sizes. Yeah? So, well, how many such vectors are there? You want degree to be less than or equal to 1. How many monomials of degree less than or equal to 1 exist in n variables? There are n degree 1 monomials and 1 degree 0 monomial. That's n plus 1 of them. Okay, so number of monomials of degree less equal 1 in n variables is equal to n plus 1. Yeah, That's how many vectors span this subspace. Yeah, that times A, of course. This. Right? So the number of vectors that span this subspace is A times n plus 1. And now we're done. And that's where this n plus 1 is. Does that make sense? Yeah? So if you see, I really didn't do anything here except use the fact that degree 3 and n variables. Correct? So if that's all I used, then the same argument should go through for this case, right? The parameterization is again degree 3, but it uses 3 times n variables. That makes sense? So if it uses 3 times n variables, you just have to replace n with 3n and you get the same answer. Does that make sense? Yeah, that's all you have to do. Now, what would you do if your parameterization was degree d? Yeah, so let's say instead of 3 tensors, you were interested in d tensors. Correct? Then in this step, where is it? In this step, the sum of degrees would have to be less equal d rather than 3. And if the sum is less equal 3, then one of the two monomials has to have degree less equal d over 2, or floor of d over 2 if you wish. Right? Let's just say d over 2, let's forget the floors. And that means out here, you would take the spans of polynomials whose degree is not less than or equal to 1, but less than or equal to d over 2. How many of them are there? Roughly n to the d over 2. There you go. Which means if you wanted to prove tensor, if you wanted to figure out the potency of rank methods for d tensors, well, it's roughly n to the d over 2, which is the trivial bound in that case. I don't expect you to know it offhand, but to try to make the most trivial bound, you'll get n to the d over 2, and you can't get much better than that.
The trivial bound is just flattening the d-dimensional thing into a matrix, and you get floor and ceiling of d over 2.
So you can get n to the d over 2, and this will give you n to the d over 2 up to some constant, because that's the number of monomials you get, which is kind of strange, right? I mean, you're arriving at n to the d over 2 in two completely different ways. One that gives you an upper bound, one that gives you a trivial lower bound. But okay, so there ends the proof. So I'm just going to stop for any questions on the proof.
It's just an obvious strategy to try to get superlinear lower bounds on 3 tensors, which would be, push them up to a 4 tensor in some nonlinear way, and then flatten.
Yeah, but then how would you pull back the fact that, yeah. Right.
Well,
So,
if you beat them up to 4 dimensional and then send them to flatten them to 2, and both are linear, then this is already
right, so he doesn't want to send it up to 4 tensor in a linear way. He wants to do it in a non-linear way.
First one is non.
Yeah, first one is non-linear.
Right. So you can do it in a non-linear way, but now I have to ask you, how will you pull back a lower bound with this non-linear map? This is the heart of it. So if you start out with a degree 2 map instead of linear, then it kind of disappears, right? Because then this would be, if phi was degree 2, then this is a degree 6 map, and then monomials of degree 3 is n cubed or something. The argument sort of disappears.
Yeah. How does it give you a low bound?
Yeah, but
I don't know how to use nonlinear methods in this context to give low bounds. So it seems that that's what everybody's using, linear methods, and these linear methods don't seem to. You cannot give low bounds. What?
Also, you can't get an n squared lower bound actually. The most is n squared over 3 or something. So if you just start.
Yeah, but there might be a cost associated to it. It's not so. So it's kind of clear that the only thing that you ever want is the parameterization, right? That's the only thing. But here's a different point of view on these parameterizations. And okay, so you think this degree D parameterization, degree 3 or whatever you might think is just some feature of the parameterization. But let me tell you is, what is the definition of tensor product? The definition of tensor product is something that says is this universal object that converts multilinear maps to linear maps. Does that make sense? So maybe let me do it with polynomials. Okay, so degree 3 polynomials is an object that converts degree 3 polynomial degree 3 maps from linear forms to linear maps. Okay, so let me write this. Poly n3, this is a universal object that converts degree 3 maps from the set of linear polynomials into whatever vector space you like, or even whatever object that can take a degree 3 map, and converts this to a linear map. Poly. Yeah, to a linear map from poly n3 to this. This is a very funny way of writing it when you write it in polynomials, because it gets more and more confusing. And this is where I will do a slight switch of notation, and let me see how I want to write this. So the way I want to state this as some kind of advertisement for algebra is degree 3 maps. Okay, so this is maybe linear polynomials, I don't care, it's some vector space. Okay, so degree 3 maps from a vector space into something is equal to degree 1 maps or linear maps from what I write as the third symmetric power to that same thing. Okay, so the 3 is far more canonical in this situation than just the parameterization. Okay, and if you look at it in this situation, what it's saying is that linear maps from here are the same as degree 3 maps from here, right? Which means this L contains all the information that phi should have. This is just philosophically happy, right? You know that you've not lost any information. You know that you're using all the information that's there, right? Just looks in a different way. And the same thing for tensors. So, but okay. So this is a subtle point that I want to make. Is for 3 tensors it doesn't really matter, but when you go for higher tensors you can do a little bit more of an improvement. Okay, and the way I will improve it is I will tell you what the tensors are a universal object for. Okay, so let me be the blah blah. So let's say D copies, right? This is the universal object that does this. It takes multilinear maps and converts it to linear maps. Does that make sense? So when I say multilinear, you mean multilinear in each one of these guys, right? So it's not just a degree D map, it really is a degree 111 map. That makes sense? Which means, when you were trying to do this kind of variable matrix, right, where you plugged in the variables, the entries are not just degree D, but they're actually degree 11111. So it's a further restriction on the set of monomials that can actually appear, right? So the monomials that can will also be this kind of multilinear. I think people call it set multilinearity, okay, in this concrete world. And so that's a smaller set of monomials, so you get a better bound. Yeah, the exponent doesn't really change, but it's a better bound. Yeah, so you can use all kinds of features that you have. But this also tells you why tensor rank and Waring rank are particularly nice, because the parameterization encodes the universality of the object that you're trying to study. Yeah, for another set to depth 3 circuits or something, there is probably some vague loss of information somewhere that we don't really understand between the parameterization of the simple and the actual set itself. Okay, that's a little bit of advertisement for algebra. And now I want to so I expected a slightly different audience, but I don't have it, so I have to skip certain things, but I will point out another way you can come up with this count of 2 times n plus 1. Okay, and I will try to do it sort of briefly. I don't want to talk about the extension. What's the point? I mean, okay, so the extension part is simple. Okay, one way to look at this is such kind of rank methods is you're lifting matrix rank lower bounds to Waring rank lower bounds. Yeah, and in that sense, this is a barrier to lifting result. It says you can't lift matrix rank lower bounds to get Waring rank or tensor rank, whatever it is. Then you can ask the question, what if you try to lift 3 tensor lower bounds to 4 tensor lower bounds? Yeah, and the answer is you can't do it either. Okay, you can't get any improvement beyond a constant. And you can do this whole game where you can take any 2 different ranks that you want and ask whether you can lift it or not. And part of this, there's one issue that shows up. And the issue that shows up is right here in the symbolic step. The point was here I said some argument with minors and blah, blah, blah. Correct? There are no minors if you have tensor rank or Waring rank or some other measure that you have. Okay, so you have to struggle. And there's a struggle there, and that struggle involves going from the function field to its closure. Okay, but now what does the closure of the function field look like? Nobody knows. Yeah, and so in this case you were happy that there were rational functions to power series. Yeah, you could do something with rational functions and you could go to power series, right? Now you have things in the closure, and you still have to find some way to make them power series. And this can be done. It's not, it can be done if you know enough things. Okay, it's an
I think there is still a philosophical issue to point out. So the context for all barriers, I don't know, for people who know natural proofs, is that the only way we can prove lower bounds is using methods that we understand. And understand means they are simple. We can efficiently compute them, like matrix web. That's sort of the philosophy. That, the reason we cannot prove lower bounds is complexity. It's our own complexity barrier. So this extension, at least hypothetically, allows you to try to prove lower bounds by things we have no access to. Not by matrix rank lower bound, but by optimal tensor rank lower bound, which God gives us. And even this is not controlled.
But still the math is from 4 tensors to 3 tensors is linear.
Yeah. Otherwise, yes, absolutely. Yeah.
I mean, yes, you're
that's a very good point.
you're expecting God to give you 3 tensors, but you're not expecting to give you an extra new method to solve it, right? Okay, so I've got to talk about some things, and feel free to not look at it very deeply. Okay, I'm just going to point out another way of arriving at the same number in some weird way. Okay, and this weird way will be a slight roundabout, but let's see where we can get. So V will be the span of a bunch of variables, let's say x1 to xn. Okay, so these are the same variables that you want to think of in the polynomials of degree 3. Now I want to look at the coordinate ring of V, but I want to give it a slightly funny notation. Okay, so when I say coordinate ring, I mean V is a vector space. They have coordinate functions, right? Coordinate functions are linear functions. Polynomials and the coordinate functions are polynomials. And the coordinate functions I want to write in this really funny fashion, because I want to interpret it as derivatives. Okay, so this thing has, this is the coordinate ring, the ring of polynomial functions, let's say, on V. This has 2 roles. Okay, so this has 2 roles. The first role is, it's the coordinate ring, of course. sorry, it has two roles. The first is it's the ring of polynomial functions on V. And it has a second role, which is it acts as differential operators on, well, you don't want to act differential operators on just linear guys, on the ring of polynomials here. Okay, and in the most naivest way you can think of, you put a differential operator, you put a monomial, you do whatever you did in calculus 1. And then there's this really funny lemma that that has always bothered me, and it's called the apolarity lemma. But to talk about the apolarity lemma, I have to first tell you what this thing is. So if I take some polynomial of degree d, yeah, which in the earlier notation this would be poly nd, n variable polynomial, then I define the annihilator ideal. Yeah, ideal is a big word, but forget the word ideal. This is going to be the set of all differential operators inside this ring which kill my polynomial. Set of all differential operators that kill the polynomial. That makes sense? Right? So that's this role that's being played. Okay? The apolarity lemma says this f is
Make sure that if f is a univariate polynomial of degree d, then you simply have any, in this idea you will have all the differential operators of degree at least.
yes.
D plus 1.
Yes. That's right. Yeah. So all the differential operators of degree d plus 1 exist in this ideal, but there will be also some in smaller dimensions. Like if f is x1 to the d, then you take differentiating by, you take del 2, you will kill it. Yeah, there's a lot more of them. Anyway, so the lemma is somehow that f is in the span of a bunch of linear forms, d forms of dth powers of linear forms, if and only if.
This just means that the rank of f is most r.
Yes, but it's more specific.
The world's long rank.
Right, but it's more specific. It's saying it's in the span of these particular r things. Yeah, in particular, it would mean that the Waring rank is less than r. Okay, if and only if the ideal is contained in this annihilator ideal. Okay, and here is where this. Okay, so, right. So this is okay. So z is going to be this guy, which is you take this. You take these points inside. Let me not do this. Let me put it in a different way. How do I want to say this? Okay. So then I have no choice but to tell you a little bit of. So z is going to be the set of points L1 to LR inside this vector space. Okay, so I have the span of these polynomials. I take just the linear polynomials in there. Okay, but I also take all scalings of it. So it's a bunch of lines. That makes sense? The right way is to view it in the projective space and it becomes a bunch of points. Okay, so it's a bunch of lines. So this is a subvariety. It's a subset. And you look at all the polynomials that vanish on it. This forms an ideal, and that's what this guy is. Does that make sense?
So Z is not finite here?
It's finite if you look at it in the projective sense. Otherwise, it's linear. So you would take the homogeneous coordinate ring as a homogeneous ideal rather than. Anyway, so I don't want to get into that. I don't want to teach people projective geometry.
Left side, but there's no D on the right side.
Yes. Yeah, it's another thing that that makes it kind of strange. But the D somehow is captured within this.
Oh, you're assuming F has D.
That's right. You're assuming F has degree D. Okay. So it's a very weird thing, and it's not. I don't like it because this same ring is playing two different roles. On one side, it's acting as some differential operators on your function. On the other side, it's acting as coordinate functions on linear forms. And if the set of all differential operators when acting as coordinate functions kill all these points is a subset of all the all the operators that kill f, then it's the same thing as f being in the span. Okay, it's a long thing. It's a long-winded thing. I don't have.
Proof, I guess, is just. I mean, it's simple, right? It's not a.
It's simple. You can do it. It's not particularly hard, but again, it's still not revealing as. I still don't understand why something like this works. Okay, but let's not get into that. What I want to point out is this particular calculation. I want to ask. So this f annihilator ideal. It's an ideal inside this guy, right? And I want to ask, what is the dimension of the quotient? Okay, what is the dimension of the quotient? Well, the best way of doing this is from this ring, which is a vector space. It might be infinite dimensional, but I don't care. Okay, to functions, you have a map that takes some differential operator and applies the differential operator to f being the polynomial that you have. Does that make sense? And the kernel is precisely this annihilator. Rank nullity theorem. Yeah, the dimension of the quotient is the dimension of the image. Does that make sense? Okay, so this dimension is equal to the dimension of image of. Well, what is the what is the image? You actually know what this is. You're applying all partials. This is the space of partial derivatives. Does that make sense? Okay, so this guy here is the space of partial derivatives. Okay, so now let's just assume f is degree 3. Can you give me an upper bound on this dimension of the space of partial derivatives? And you get exactly the same idea. The idea is, do you want to go for it?
Order n squared.
No. I'm leading you up to it, right? I'm leading you up to a number that you should come up with. So here's how you do it. Okay, so there are two cases. Either you're applying partials of degree less equal 1. Let's just say monomials, right? Monomial operator. Either you're applying monomial operators of degree less equal 1, or when you apply something of larger thing, you will end up as a polynomial of degree less equal 1. Yeah? The two things split, and that's the same count you get. So it's just a completely different way of arriving at the same answer. And in some sense, there's a rigorous way to give this also as some sort of barrier to rank methods. At the moment, it's in a far more constricted case than the result that I just showed you. But this also, when put in a certain language, will give you another kind of barrier result, which at the moment is not as strong as the one that we already know, but it exists. Now, all